The same embeddings can return different nearest neighbors just by changing the distance metric. We'll compare cosine, dot products, and Euclidean distance and show when each ranking is valid. You'll understand the pattern behind a pipeline that ranks vectors with competing distance rules and chooses one based on size effects. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Every search or retrieval system that uses embeddings answers the same core question. Which document is most relevant to this query? Engineers reach for cosine, dot product, or Euclidean because each feels intuitive in different setups. Cosine focuses on angle. Dot product rewards both angle and length. Euclidean cares about straight line closeness. The pain point is that switching metrics can reorder your top results without changing the text at all. That leads to confusing A/B tests and inconsistent chatbot answers. Understanding when each metric is valid saves debugging time and improves user experience on retrieval-augmented generation pipelines. At a glance, cosine compares direction only. If two vectors point the same way, they match, even if one is longer. Dot product multiplies length and direction, so a longer vector can win despite a slight angle difference. Euclidean looks for the smallest geometric gap. Picture one document vector as a long arrow and another as a shorter arrow in the same direction. Dot product prefers the long arrow. Cosine treats them as equal, and Euclidean picks whichever is geometrically closest. Those are the behaviors we'll make visible. We will build a tiny experiment that embeds a handful of short documents once, inspects their lengths, ranks them 3 ways, then shows how scaling a single vector changes the winners. Finally, we will encode normalized vectors and pick a simple rule that chooses the right metric automatically. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To start, we need raw embeddings and a stable baseline that every ranking will reuse, so we can compare apples to apples. This snippet creates the raw vectors that every later ranking will reuse. In a RAG pipeline, the first hidden choice is whether your embedding vectors are normalized before they reach the vector database. SentenceTransformers is doing the real embedding work through model.encode, and normalize embeddings false keeps the original vector lengths intact. The same query and docs are kept short, so the ranking changes stay easy to see on screen. The code prints the number of documents and the vector dimension to confirm the search inputs are ready, which is helpful before any ranking or scaling steps run. Now that we have raw vectors, we should check whether their lengths vary enough to matter for dot product scoring. This example measures how much vector length differs across the raw document embeddings. Engineers often treat embeddings as only directions, but dot product also rewards magnitude. np.lineout.norm gives one length per document vector, then spread makes the range visible without dumping a full array. The code chooses long I and short I to identify which documents sit at the extremes, which is the first clue that metric choice may affect retrieval. The output prints the largest raw norm and the norm spread, making magnitude an explicit retrieval signal you can reason about before choosing a metric. We can now compare rankings from cosine, dot product, and Euclidean to see whether they agree on the top hit. This code ranks the same SentenceTransformers embeddings 3 different ways. Copying a database default feels harmless when all 3 winners match, but that agreement is something to verify, not assume. The snippet computes raw dot products, cosine scores by dividing by both vector lengths, and Euclidean distances, which are flipped to higher is better by negating. A helper top by picks the highest scoring document for each metric, so the comparison focuses on the visible winner, instead of a full scores matrix. The printed results show whether the three metrics pick the same top document, which establishes the baseline before we introduce magnitude changes. If the metrics disagree or margins are small, we can force a controlled change by scaling one document and observing the effect. This snippet makes the magnitude problem visible by scaling one existing document vector. The scaled vex change is a controlled teaching probe, not a recommendation to modify embeddings in production. By multiplying one document vector by a scale factor, dot product sees the bigger vector length and may promote that document, while cosine divides the length back out and keeps ranking by direction. That difference is exactly what can surprise teams when one index stores normalized vectors and another stores raw vectors. The printed output highlights that the dot product winner now diverges from the cosine winner, which explains why normalization must be an explicit part of your metric decision. Once we see the divergence, we can formalize a simple retrieval rule based on whether vectors are unit norm. This code turns the lesson into a small retrieval rule you can carry into a RAG baseline. SentenceTransformers model.encode is called again with normalize embeddings equals true. So the vectors are intended to have unit length before scoring. When unit norms confirms that condition, rule chooses dot on normalized. Otherwise, cosine is the safer choice because it handles length inside the metric. The code then uses a simple dot product to compute scores over unit docs and selects the top document. The printed output shows the selected metric rule and the retrieved document, tying normalization directly to the search metric and making the decision reproducible in a pipeline. In a real system, this toy mapping is straightforward to scale. Use the same rule when ingesting a vector store. If your encoder outputs unit length vectors, dot product is efficient and simple. If you cannot guarantee normalization, prefer cosine to avoid accidental length bias. And always log vector norms during indexing so you can detect when magnitude will influence retrieval. What it is: 3 common ways to rank vectors that differ by whether they use angle, length, or straight distance. When to use each: pick cosine when relative direction matters and lengths are uncontrolled. Pick dot product when your encoder intentionally scales important documents. And pick Euclidean when absolute geometric closeness is the right notion of similarity. 1 caveat: inconsistent normalization across encode and index steps is the most common source of surprising re-ranked results. To extend this example, rerun the experiment on your actual document corpus while toggling normalize embeddings, and measure top 3 agreement between metrics. That single check will reveal whether your embedding pipeline needs normalization, metric change, or both. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.